Hello everyone. We're discussing constructive and destructive interference. We have so far developed this important part. Path difference delta x. It is n lambda where n is 0, 1, 2 and so on for constructive interference. This path difference delta x is 2n minus 1 lambda by 2 where n starts from 1, 2, 3 and so on for destructive interference. For constructive we take n from 0. For destructive we take n from 1. And you will understand this when we go through YDSE, which is Young's double slit experiment. That's what we are going to discuss in today's lecture. This much we have already done in previous class. Now, write down Young's double slit experiment. In short, Y D S E. The thing is, what is double slit? We'll understand this part first. You know that if we have a source S1 and waves coming from S1 are like this. This is some point P. This was the position of S2. Waves coming from S2 are like this at point P. You know that this S2 is also at this place. Just so that you can understand it, I am drawing it under the S1 wave. This was the case for constructive n equals to 0, your path difference is 0. So, in this situation, you will expect that constructive interference is going to happen, which is correct also. But what if this second source S2, it emits a wave like this? I hope you can see the blue color. If you cannot, this is in blue. Now, S1 is sending a black wave. Black means top and then the bottom. Whereas S2 is sending bottom and the top. Like this. Now, if we interfere this black with this blue, then although path difference is 0, we will get destructive interference. This will be cancelled by this. Similarly, this bottom will be cancelled by the top. If we have two independent sources, then we have no control over this thing. Which one sends black one or which one sends blue one, there is no control on this part. Top, bottom, bottom, top. It can be any combination. For example, this S1 can decide to send a wave like this. Basically, there are electrons which are jumping from high energy orbit into the low energy orbit, and in this process some energy is being released, and therefore you need to somehow make sure that for constructive interference black interferes with black, or if S1 is sending blue, then S2 must also send blue. Blue and blue, when they interfere, again you can see that they are supporting each other. If we get an interference like this between black and black, between blue and blue, then you will get a stable interference pattern. Otherwise, what is going to happen? Just imagine this. The very first pulse sent by S1 is of the black type. From S2, again black. So this black and the black, they are going to produce a constructive or bright interference. Bright fringe will be received at point P. Next pulse is black and coming from S2 blue. So it will be black and blue. That means this will be cancelled by this complete darkness. That means what? Sometimes you will get brightness, sometimes you will get complete dark spot at a given position on the screen. Which means on an average a bright spot, dimly bright spot will be present. Whereas for constructive interference, what we expect? This interferes with this. Blue interferes with blue, so that all the time we get constructive interference and bright spot is really bright. So how do you make sure that something like this happens? Black and black, blue and blue. There is a technical word for this which is called coherence. This double slit makes sure that both waves coming from S1 and S2, they are coherent. Coherent means they always maintain a particular phase difference between them, and this phase difference never changes. We'll write all these things, but just wanted to explain the meaning of coherence with the help of this example. The same thing happens with the destructive interference also. You know that this was the case for destructive interference, as we discussed this thing in the previous lecture. This was point P, and we had started wave from this part. This was S2, lambda by 2 behind, which is the n equals to 1 case. So if this black interferes with this black, you always get what? Destructive interference or dark fringe. What if S2 decides to send a wave like this in blue? S1 is sending black, but S2 decides to send a blue wave. This black, when interferes with this blue, you can see they both are what? Bottom, bottom. That means they are interfering constructively. And therefore, instead of dark, you will get what? Bright. So if we have no control over this pulsation, then there will not be a stable interference present on the screen. If we can make sure that S1 sends black and S2 sends black, or if S1 sends blue, then S2 also sends blue, then you'll always get what? Destructive interference. Blue and this blue in this case, they will always cancel each other. Black will cancel this black. So this type of system where S1 and S2, they are interrelated, it's called a coherent system. Write down a few points, and before that draw this figure as well as this. Make sure that this is a different color, blue or whatever color you choose. This and this should be of same color. This and this should be of same color. We'll call it figure 1. This is figure 2. This is blue and this is also blue. Draw this much. Write down these points. In figure 1, if black interferes with black, whatever color you are choosing, you can write that. If black interferes with black, then constructive interference takes place at P. Constructive interference takes place at P. And a bright spot is observed. And a bright spot is observed. But if S1 sends black and S2 sends blue, S1 sends black and S2 sends blue, then these waves will cancel each other, then these waves will cancel each other and destructive interference takes place at P. And destructive interference takes place at P. And a dark spot will be observed. And a dark spot will be observed. If we have no control over S1 and S2, if we have no control over S1 and S2, then these bright and dark spots, form so rapidly. Remember the number 10 to the power 15 oscillations. These bright and dark spots form so rapidly that we only observe average brightness at point P. That's what is happening everywhere near you on the board. There are multiple light sources. They are sending their light waves, but you never see a dark spot. There are times when waves are cancelling each other. The very next instant, they are supporting each other. The very next instant, maybe they are cancelling each other. It depends on the way waves are coming. We have no control over these things. It can be bright, dark, bright, dark, anything. And therefore, these things since happen at a rate of 10 to the power 15 oscillations per second, you will find what average brightness, which happens everywhere near you and on the board also. Whenever you have two light bulbs, when you switch on these two light bulbs, you always find that there is no spot which is completely dark. You're finding what average brightness. If you could produce two bulbs which are always sending waves like black and black or blue and blue, if you can arrange them in this manner, then you will find that at places you have maximum light and at places you have no light or low intensity light. Similarly in figure 2, we expected dark fringe at point P. Why did you expect it? Because of this lambda by 2 path difference. Similarly in figure 2, we expected a dark fringe at point P, but if S1 and S2 send wave pulses independently, then again average brightness will be observed. At point P. Now write down the heading coherent sources. Write down the coherent sources. Coherent sources are those sources Coherent sources are those sources which have same frequency, what you are looking here is lambda. So if you have same lambda, you will definitely have same frequency. Coherent sources are those sources which have same frequency and they always maintain a fixed phase difference with each other. Now try to understand this fixed phase difference with each other. Suppose we decide that S1 will be sending black and S2 sends blue. We have made a setup in which S1 always sends black and S2 sends blue. Then what do you get at P? Dark. What is the phase difference between black and blue? Up and down, pi, 180. Next time when S1 sends blue, they have to maintain a fixed phase difference and therefore S2 will be sending black. So if this blue interferes with black, you get what? Dark. So if you can maintain a phase difference of pi between S1 and S2, up, down, down, up, then you always get what? Dark fringe. S1 and S2, they are always maintaining pi. They will be called what? Coherent sources. Next, suppose S1 sends black and S2 sends black. Up, up. What is the phase difference? 0. Next time, S1 sends blue, S2 also sends blue. What is the phase difference? 0. Initial phase difference. Down, down. That means what? Black, black. You will get what? Black interferes with black. Same type of waves. Constructive. Bright spot. Blue, blue. Same type of waves. Again you get what? Bright. If you can maintain a given phase difference 0 or pi or any other all the time, then those sources are called what? Coherent sources. If sources are not coherent, they are independent, they are independently working sources, two independent light bulbs, then you will never get a stable interference on the screen. Write down this. Let's take this example from these figure 1 and figure 2 only. If in figure 1, S1 sends black and S2 sends black, that is, phase difference between S1 and S2 is 0. At point P, constructive interference takes place. But if S1 sends blue and S2 also sends blue, again phase difference is 0 and a constructive interference takes place at P. A constructive interference takes place at P. then S1 and S2 are called coherent sources. Then S1 and S2 are the coherent sources. Well, one of you is saying that audio and video is not clear. Is this the problem with everyone? So some of you are saying that no, that means those who are having this audio and video problem, disconnect and reconnect, and maybe the signal quality will improve then. And if you find that video quality is again not that good, do tell me. I will also disconnect and reconnect. But since some of you can see things clearly, most probably problem lies on your side. So if they are sending black and black, blue and blue, S1 and S2, they become what? Coherent sources. What are coherent sources? They always maintain a given phase difference. Let's understand this with the help of S1 and S2 in figure 2 also. And there is no need to write again and again same type of thing. Just pay attention. If S1 sends, we have designed this particular setup for destructive. So what we wanted, S1 sends black, S2 sends black. What is the initial phase difference? 0. Up, up. Between S1 and S2, initial phase difference is what? 0. At P, black interferes with black. Cancellation, destructive interference. If S1 decides to send blue, S2 is also sending blue because they are coherent. They always need to maintain 0 phase difference, same phase difference throughout. Blue and blue, when blue interferes with blue, again a cancellation takes place. You will get what? Destructive interference always. Only requirement was that S1 and S2 should maintain what? A constant phase difference of 0 with each other. Now, if we say that S1 sends black and S2 sends blue, things will be much more clear. Now, if S1 sends black and S2 sends blue, what is the phase difference? Pi. We have no issue. If you have phase difference of 0 or pi, the thing is, if you can maintain this phase difference throughout, then you will get a stable pattern. So if S1 sends black, S2 sends blue, black interferes with blue, and you get what? Constructive interference. Black with blue. What was the phase difference right here? Pi. Now, next time S1 starts sending blue. If it sends blue, it has to maintain a phase difference of what? Pi. S2 therefore sends black. Now, this black and this blue, when they interfere, you're getting what? Constructive interference. Which means what? If between S1 and S2, phase difference in this particular setup is 0, you get dark fringe. If between S1 and S2, phase difference is pi and it maintains this pi, then you get what? Constructive interference. Now, if you understand meaning of coherent sources, then write down yes in the comment box, and then we'll start discussing Young's double slit experiment. Now look, how do we produce coherent sources? Take a cardboard, make two slits in it. They are very thin, narrow slits, but just so that you can see them. Very narrow slits. I hope you can see the slits. We have made two holes in a cardboard basically. Here lies the screen on which interference pattern will be observed. This is the screen. I'm just drawing a simple figure. We'll start YDSE. This is basically setup of YDSE, but we are trying to understand the meaning of again coherence with the help of this particular setup. We have a light source, and what this light source does, it sends light waves at this point. This is the center of the screen. We have specially chosen the center point so that path is completely same. What does it mean? Look here. If S sends a wave like this, this is a wave coming from S. We'll call this upper slit S1. Main source of light is S. This will be called what? S1. This will be called S2. S is sending a black wave, means pulse starts like this, up and down, up and down. So the S2 also receives the same thing. And what happens? These pulses down, down, they interfere at this point and produce what? Constructive interference. Now, we have no control over this wave pulse. Second wave, which is coming from S, it can be of black type or it can be of blue type. Hopefully you see the colors and all. Blue, blue. Now, we have no control over S. It can send black or it can send blue. But now the advantage is, if S sends black, then S1 receives black wave. S2 also receives black. Black and black, when they interfere, they are producing what? Constructive interference, bright spot. Next time S decides to send blue wave, blue, blue. S1 receives blue, S2 also receives what? Blue. When blue interferes with blue, again what? Constructive interference takes place. So, S can send any type of wave, black or blue. We have created two coherent sources. S1 if is black, S2 is also black. If S1 is blue, S2 is also blue. What happens here? We don't have to worry about it. This is double slit. And why is double slit used? So that S1 and S2 they become what? Coherent sources. Draw this figure and then we'll write a few lines. Write down this. In the given figure, source S can send any type of wave, black or blue. We have no control over it. But if S1 receives a black wave, receives and then sends it, receives and then sends it. If S1 receives black wave, then S2 is also receiving black wave. And similarly, if S1 sends blue, then S2 also sends blue. This way, S1 and S2 become coherent sources. This way, S1 and S2 become coherent sources. And this is the reason we use double slit. If you remove S and you have two independent sources, then two independent sources are never coherent. There will be the same problem: black, black, blue, blue, black, blue, blue, black, any combination. If S1 and S2 are what? Non-coherent sources. If you have made them coherent, how do you make these things coherent? That's the way of doing this. Then you will always get a stable pattern. Right on this point also, two independent sources are never coherent. Well, nowadays you can make two independent lasers coherent, but as far as your 12th level thing is concerned, two independent sources are never coherent. We'll continue using this statement. Two independent sources are never coherent. And therefore, if instead of S We choose independent S1 and S2 light sources. We choose independent S1 and S2 light sources. Then interference on the screen will be unstable. Interference on the screen will be unstable. Now let's produce exact working for all this. This is S, this is S2 or S1, and this is your S2. In this setup, we are having S1 and S2 at the same distance from source. In general, they can have any type of separation. This point is O, center of the screen is O. Take any random point P. A wave starts from S and moves like this. I will use simple ray diagram for this. That's how wave is coming. In reality, you know, you're getting all the pulses. Another wave coming through S2 reaches P. And interference takes place at point P. This separation between screen and slits is called capital D. Separation between S1 and S2, between the slits. S1, S2 is D, and D is much smaller than capital D. Capital D is very large as compared to this small separation. This is the position of point P with respect to O, which is given by X. We just want to find out path difference between these two at point P in terms of X. Suppose somebody says that X is 1. If X is 1 and we find that path difference is lambda by 2, then we immediately know that if it's lambda by 2, we're going to get destructive interference. For some other value of X, let's say 2, we found that path difference is coming lambda. If path difference is coming lambda, then we know that constructive interference takes place at that particular position. So if we can find path difference in terms of this X, path difference between this and this light wave in terms of X, then we can easily mathematically define the condition for interference at point P. Now, when I say that this capital D is much larger than small d, well, first look at the path difference. Path difference. We define path difference with delta x. This is S2 plus S2P minus SS1 plus S1P. What is the first? This path SS2 plus S2P. I've taken the larger path first. And the smaller one is what? SS1, S1P. In this setup, SS1 and SS2 are same. In some other setup, they may get some other value, but right here, in this particular setup, SS2 and SS1 are same, and therefore this path difference is only S2P minus S1P. So if we can find path difference from this position between this line and this line, starting from S1, starting from S2, if we can find that, that will be the only effective path difference for us. Now, how do we do this? Try to visualize something over here. If I say that we have got two sources which are very close, I hope you can see the dots. In real setup, dots are even much closer than this. And there is a point on the screen where you are getting these two light waves. Light waves are reaching from S1 and S2 at that point. In reality, this separation is even less and this is even larger. But you will get an idea about it. In this type of setup, if we need path difference, what we do, we drop a perpendicular. If you drop a perpendicular like this, then up to the foot of perpendicular, this and this, they become what? Equal. What is happening? Look here in the larger figure. If I drop a perpendicular from S1 onto S2P, and if it falls at M, this is a perpendicular, then we are saying that S1P is approximately equal to MP. This will not be true if a setup is exactly like this. If somebody keeps a light source here, another light source here, and a screen over here, then look at the triangle. In this triangle, you will never find that this length is equal to this. But if you decrease the separation between S1 and S2 and you increase this separation, then this will become S1P almost becomes what? MP. That's what I have shown here. Now, what is the advantage of doing this? So if you are saying that S1P is equal to MP, then what is the path difference? This is the path difference. This much. This is your path difference. These two are equal. These two are equal. So what is the extra? S2m is the extra thing. So this S2p minus S1p is simply S2m. So aim is to find S2m. Note down this much and then I'll erase some parts from it, and you can draw everything again as a new setup. But first note down everything like this. And for your understanding, you can also draw figure over here. The equal sign, they are saying that up to the perpendicular point, both lengths are same. This is the extra portion. If you can feel it, if you can feel or see this thing. What is this? Zoom in and you get this. One of you is asking that why the path difference is from S2, why not from S? We have taken it from S only. What I told you that SS1 and SS2, they are equal. You are taking path differences from this point. If somebody decides to place light source closer to S1, then you have to count SS1 and SS2 separately. In this particular setup, SS2 and SS1 are same. S is equidistant from S1 and S2. That's the reason. This is not the restriction. You don't have to have always a setup like this. If somebody decides to, if you decide to have a setup like this is S1, this is S2, and this is S, then light will travel this, light will travel this, and then it will reach the point. So in this case, you cannot take path difference from this and this only. You have to consider this as well as this, both. Remember these values, we'll be using these values. So remember this. This is M, and we need to find S2M. Position of P is given with respect to center point of S1, S2. Or you can say S1 or S2 because the separation between S1 and S2 is very, 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 very small. So how do I locate point P? Should I locate it with respect to S1 or with respect to S2? We say that we locate point P with respect to the center of S1 and S2. Where is it located? At an angle of theta. The whole thing is in red. If you can see the colors and all. This red line is giving you angular position of point P. Now this is theta, then this angle is also theta. Why? Look. This red line with horizontal, its angle is theta. This is theta. With the horizontal red line, its angle is theta. Now, this and this separation is very, very small, and therefore we can say that even this angle is theta, approximately. This and this. S1 and S2, they are close to each other. This is theta, this is also theta. So if you say that this is theta, if this is theta, again, we have dropped a perpendicular. We are saying that this angle is theta and this is the perpendicular. This is theta. You can see this much will be 90 minus theta. I hope it's visible. This is theta, vertical, horizontal, theta. This is 90 minus theta. Now, we have dropped perpendicular and therefore this is nothing but theta. Simple geometry. So, this angle is coming theta. If this is theta, then S2M is simply d sine theta. Vectors. What is S1, S2? Small d. This angle is what? 90. So what is the perpendicular component S2M? This perpendicular component. Perpendicular component is what? D sine theta. All this geometry was to find this d sine theta part. So we have found that S2M is d sine theta. Now, if theta is very small, which it is, it's not this large, theta is very, very small. Just so that you can see everything, we have drawn these large values of theta, but theta is close to this point O. If theta is small, then sine theta can be approximated with theta. Many a times we have used this thing starting from 11th. If theta is small. If theta is small, then theta can be approximated with tan theta. If you wish, you can write like this. If theta is very, very small, then sine theta can be approximated with theta, which can be approximated with tan theta, which is like sine 0 is 0, which is also tan 0, which is not correct for sine 30 is not 30, in fact pi by 6, which is not equal to tan 30. Only if theta is very small, we use a relation like this. Now, why did we use this relation in this figure? Because once I say tan theta, what is tan theta now? Look at the larger figure. Tan theta is perpendicular x divided by base, which is capital D, and therefore this d tan theta for me is perpendicular upon base. What was the aim? If you remember, we wanted to find path difference at point P in terms of x, and that's what we have done. We have found the path difference in terms of x. Small d divided by capital D multiplied by x. Note down this. And if you wish, you can draw these figures also as a separate note. Our aim was to find this part. All those who feel comfortable up to this point, write down yes in the comment box. If you have understood this small d x upon capital D, then write down yes in the comment box. Good. Look here. For constructive interference or bright fringes, the bright spot is called bright fringe. Delta x, which we have found is x d upon capital D, should be n lambda. This gives us x as n lambda capital D upon small d. And starting from 0, 1, 2, 3 and all. This is the position of bright fringe from O. When I put n equals to 0, I get x equals to 0, that is O. For n equals to 0, we are at O. This is 0, this is O. For the center of the screen, this 0 corresponds to central bright fringe. I think it's visible. This is 0, this is O. So at O you get what? Central bright fringe. What is central bright fringe? The place where path difference is 0. If n is 0, this ax becomes what? 0. At O you get what? Central maxima. This is also called maxima. Maxima. And then that central maxima will be followed by a minima, which is dark fringe. Why? We'll see that. After that you will get first bright fringe. Then you will get a minima, a dark, and then you will get a second bright fringe. So n equals to 0. At O, we have got central bright fringe. 1 is for first bright fringe. 2 is for second bright fringe. And so on. Note down this fast. Look, this was for constructive. For destructive interference or dark fringe, destructive interference or dark fringe or minima, delta x, which is given by x small d upon capital D, was what? 2n minus 1 lambda by 2. This gives us x as 2n minus 1 lambda capital D upon 2d, where n starts from 1, 2, 3 and so on. That's the reason we do not choose n equals to 0. If somebody decides to use 2n plus 1, they can start with n equals to 0, but that makes no sense. The problem will be n will be 0 and you'll be calling it first minima or dark fringe. Whereas now, once I put n equals to 1, this is 2n minus 1, which is 1, the very first thing, lambda by 2, that gives us what? First dark fringe. Now try to understand the whole thing. Hopefully you have written this first, second, right. With this also you can write, this is what? First dark fringe. N equals to 1 will give you first dark fringe. With 2, write down second dark fringe. 3, third dark fringe, and so on. Now let's understand this part first. Look at these values. The values of x which you get, they are what? 0, when n is 0. When it is 1, you get lambda d by d. When n is 2, you get what? 2 lambda d by d, and so on. Right here, what are the values of x? When it is 1, you get lambda by 2 d by d. When this is 2, 2 into 2, 4 minus 1, 3, you got 3 lambda by 2 d by d, and so on. Now, when n is 0, in this case, you got what? Central maxima, central right fringe. After 0, what will be the value of x? Lambda by 2. Forget about d upon d for the time being. Lambda by 2. This is your first dark fringe. Position of first dark fringe. After lambda by 2, you get what? Lambda. This is your first bright fringe. After lambda, you get what? 3 lambda by 2. After 3 by 2, 1.5. After 3 by 2, you get what? 2. So that's how the sequence works. So at the center is your central maxima, followed by first dark, followed by maxima first, then dark, then bright, and so on. And we'll draw this fringe pattern in the next class. This much is for the position of maxima and minima, bright fringe or dark fringe, constructive interference or destructive interference on the screen. Hopefully you understand everything which we did in today's class. If you find something is difficult, then you can request for the recording of the lecture and I'll give it to you. But things are not difficult. Pay attention to everything and you will find that this wave optics thing is as easy as is the ray optics. Put all this and then you can leave. Thank you very much.